frequency response plots are being drawn for any given system to determine the relative stability. The various plots come under this frequency response plots are Bode plot, polar plot, Nyquist plot, M and N circles, etc. Bode plot is basically consists of two plots. One is magnitude plot. This plot is drawn between magnitude of sinusoidal transfer function in decibels versus frequency on log scale. The reason for frequency taken on log scale is wide range of frequencies can be considered for the analysis of the system. We can see how the magnitude variation is taking place for wide range of frequencies. So, log omega frequency is on log scale. The second plot is phase plot. This is phase angle of the given sinusoidal transfer function versus again on log scale. As this frequency response analysis is basically the system is excited by sinusoidal signal, so it has magnitude as well as phase angle. That is why Bode plot consists of two plots, magnitude versus frequency, phase angle versus frequency, and frequency is taken on log scale for the reason that wide range of frequencies we can see the behavior of change in the magnitude as well as phase angle. The main advantage of Bode plot is magnitude plot and phase angle plot are being drawn for the same frequency on log scale, and what actually we can determine using this Bode plot are gain margin represented by GM and phase margin, gain crossover frequency and phase crossover frequency. These four parameters can be determined from Bode plot, and mainly we can feel that this Bode plot actually to draw or construct it is drawn for the closed loop transfer function. And the main advantage of Bode plot, advantage of the Bode plot is multiplication terms in magnitude, multiplication terms in magnitudes are being converted into addition terms. This is the main advantage. So, when you have the terms in the magnitude transfer function, addition terms, very easy to add rather than going for multiplication. That is the main advantage of Bode plot. So, the requirement for drawing the Bode plot is g of s. Let the loop transfer function g of s is given by k into 1 plus s tau 1 by s into 1 plus s tau 2, 1 plus s into tau 3 and so on. So, the given transfer function is in S domain, and this form is known as time constant form. Though the given function, if it is in pole 0 form, it is better convert that into time constant form. So, this given function is in time constant form, but in S domain. So, we need to have the sinusoidal transfer function. So, replace s by j omega. So, this becomes k into 1 plus j omega tau 1 by j omega 1 plus j omega tau 2 into 1 plus j omega tau 3, where tau 1, tau 2, tau 3 etc. are time constants of zeros and poles. This is the way we say that it is in time constant form. So, sinusoidal transfer function is required to draw the Bode plot. So, once you get the sinusoidal transfer function, this should be written in the form of magnitude and phase angle, because the Bode plot basically it consists of two plots. So, let us write this sinusoidal transfer function in the form of magnitude and phase angle. That means k is represented by k at an angle of 0, and 1 plus j omega t1, its magnitude is 1 plus omega square t1 square. Then phase angle is tan inverse omega tau 1. No denominator in the phase angle term, because it is written in time constant form. Now, divided by this j omega is written as omega at an angle of 90 in polar form, and magnitude of this pole 1 plus omega square t2 square. The phase angle is tan inverse omega tau 2, and another pole you have whose magnitude is 1 plus omega square t3 square, and its phase angle is tan inverse omega tau 3. So, the given sinusoidal function is being written in polar form, where you will have magnitude as well as phase angle for the given sinusoidal transfer function. Now, we need to separate the magnitude terms and phase angle terms. Then you need to vary the omega for wide range from 0 to infinity, and see that how this magnitude varies and phase angle varies are to be seen from the Bode plot. Once the plot is constructed, we need to determine the stability parameters like gain margin, phase margin, etc. Magnitude and phase angle terms need to be separated, because Bode plot consists of two, magnitude plot and phase plot. So, the magnitude of the sinusoidal transfer function g of j omega is k under root of 1 plus omega square tau 1 square by omega under root of 1 plus omega square t2 square 1 plus omega square t3 square. This is the magnitude term you have, and this one we need to apply log, because the magnitude is expressed in decibels. So, when I say g of j omega in dB decibels, so we need to apply 20 log k under root of 1 plus omega square t1 square by omega 1 plus omega square t2 square and t3 square. So, when you apply 20 log, this can be rewritten this way: 20 log k by omega plus 20 log under root of 1 plus omega square t1 square. This is in the numerator term, and you have a denominator term. So, I can write with minus sign 20 log under root of 1 plus omega square t2 square minus 20 log under root of 1 plus omega square t3 square. So, the denominator terms are taken to the numerator, and there is a minus sign that is applied. So, you can see that the magnitude is having now terms of addition. So, 20 log k by omega plus 0, and this is pole, and this is also pole. So, magnitude is little complex, because there are terms involved, k by omega, then pole at non-zero location, 0 at non-zero location, etc. So, we need to understand how to draw the magnitude plot, because magnitude is taken in decibels and frequency is taken on log scale. Now, phase angle is so simple that g of j omega is equal to all phase angle terms, that k does not have any angle, but there is a 0 whose phase angle term is tan inverse omega tau 1 minus 90. There is a pole at origin, minus tan inverse omega T2 minus tan inverse omega T3. This is for phase angle function. So, you can see that in phase angle there is a omega term, and you need to substitute omega from 0 to high range of frequencies and see how it varies. And similarly, the magnitude function also we should draw for log omega. To sketch the magnitude plot, we should have a knowledge of various terms. That appear in magnitude of g of j omega is required to be known. So, the various basic factors or terms that appear in the magnitude function is constant k, then number 2 an integral factor that is k by s or k by j omega. Sometimes there may be more poles at origin, that is k by s power n, that means the function j omega whole power n. So, if integral factor exists in the given function, how to draw the magnitude plot and phase plot. Similarly, you may find a term or factor, a derivative term or derivative factor, means there is a 0 at origin along with k, say k times s, or is nothing but k into j omega. Similarly, if you have multiple zeros at origin, then it may be k into j omega whole power n. So, if you have more zeros at origin, how to draw the magnitude plot need to be seen. The next term or factor that will appear in the magnitude function is first order denominator. So, the meaning of this is 1 by 1 plus s tau. So, there is a pole, but not at origin, it is at some other location. So, for this 1 by 1 plus j omega tau. So, how to draw the magnitude plot need to be seen. Similarly, you may have a 0 at non-zero location or origin. So, it is called first order numerator term. It is simply 1 plus s into tau. It is a numerator term. So, 0 not at origin. So, it is nothing but 1 plus j omega tau. So, we must understand how the term value or in decibels varies with the frequency, and you may find little complex term, that quadratic numerator term means second order, quadratic numerator term or factor that may exist in the function, and then quadratic denominator. So, we must understand for these individual factors or terms how they vary with the frequency, so that you can combine them and you can apply for a complex problem where you may find all these 1 to 7 terms in a single transfer function, so that you can draw the combined Bode plot. So, before that we must see each and every term or factor, how it varies, whose magnitude varies with the frequency need to be understand. So, let us understand each and every term, as I said, how the magnitude of that particular term or factor varies with the frequency. Let us start with the constant gain. K. So, the g of s is simply considered as a k. Then g of j omega is also k, because it is a constant k. So, this magnitude, say A, this is magnitude of g of j omega in decibels, because magnitude is expressed in decibels, it is given by 20 log k, 20 log k. Whereas, the phase angle, say it is represented by phi, and this phase angle of g of j omega is equal to 0 degrees, because k does not contribute any phase angle. Now, when you see the magnitude, now if I want to draw the plot, the magnitude versus frequency on log scale, the meaning of this is, when I consider this as 0.1, the next division is 1, and the next division is 10, and the next division is 100, 1000, and so on. This omega is expressed in radians per second, but the meaning of log scale is each unit on x axis is multiples of 10. So, it will be 1, 10, 100, 1000, and so on. That is why Bode plot is drawn on semi-log graph sheet. Semi-log means frequency on x axis on log scale, magnitude in decibels on y axis. That is why it is called semi-log graph sheet. Even phase angle also taken in degrees. This is magnitude and this is phase angle, and it is taken for the same frequency on log scale. How the phase angle varies? Phase angle is taken in degrees. Now, if we see that magnitude term 20 log k, when k equal to 1, the magnitude A will be 0, means it is a 0 dB line. It is a 0 dB line. So, magnitude is a 0 dB line for k equal to 1. If k is greater than 1, then the magnitude is constant, but it is above the 0 dB line. If it is less than 1, the value of k between between 0 and 1, then it will have a negative dB. So, it depends on the value of k. If k equal to 1, it is 0 dB. If k is greater than 1, it is having positive dB, and if k is less than 1, then it is having negative dB. But no variation in the k, because it is independent of frequency. So, you can see that it is a straight line, it is not a function of omega. Whereas, the phase angle contribution of k term is 0. So, it is simply a 0 degree line. So, there is no phase angle graph at all because k contributes only 0 degree. So, let us see the magnitude variation for another factor, say integral factor. The meaning of integral factor is the function g of s is equal to k by s. There is a pole at origin along with constant k. Now, for this the g of j omega is k by j omega. Now, you can write this term g of j omega as k by omega at an angle of minus 90. Now, this k by omega is the magnitude term, 90 degrees is the phase angle term. So, I want to have a magnitude in decibels A. So, this is equal to magnitude in decibels. I need to apply 20 log. So, 20 log k by omega is the magnitude term, whereas the phase angle is represented minus 90 degrees. You can see that the phase angle term is a fixed value minus 90 degrees and no omega that appears in the phase angle for integral factor. Now, I need to see how this magnitude varies with omega. So, I need to consider 3 cases, that when omega is equal to 0.1 k, when omega equal to 1 k, when omega equal to 10 k. 3 values. The idea, we need to see the integral factor magnitude, how it varies for the different values of omega. So, when I substitute omega equal to 0.1 k, the A is 20 log k by 0.1 k. So, this means this value becomes 20 dB. 20 dB. Now, when omega equal to 1 k, this value is 20 log k by k, that means 1. So, it is 0 dB. 0 dB. Now, when omega equal to 10 k, it is 20 log k by 10 k. So, it is minus 20 dB. So, what do you understand here? That it is a straight line. The magnitude of integral factor is a straight line and it has a slope of minus 20 dB. Means, if you want to construct the magnitude plot A in decibels on y axis and the frequency on log scale for different values of omega, say this is 0, 0.1 k, 1 k, 10 k, 100 k and so on. Frequency is taken on log scale. So, we have seen that at 0.1 k the value is 20 dB, say this is 20 dB, 20 dB, and when omega equal to 1 k the value of integral factor is 0, and when omega equal to 10 k the magnitude is minus 20 dB. That means, you can join these 3 points. It is a straight line. It is a straight line having a slope of minus 20 dB per decade. Decade means the frequency is increased 10 times. You can see that frequency on x axis is increasing by 10. So, whereas the magnitude is decreasing from 20, it has become 0, then 0 has become minus 20. So, we say that the integral factor magnitude varies and have a slope of minus 20 dB per decade. Now, for the same frequency scale, you can actually construct the phase angle curve also, but here if you see the phase angle contribution of integral factor is minus 90 degrees. So, if I say this is 0, then minus 90 is somewhere here and it is a straight line. So, I can say that the magnitude of integral factor has a slope of minus 20 dB per decade, minus indicating it is decreasing, and phase angle is constant, it is a straight line, minus 90 degree line, it is independent of frequency. So, if you see that if there are multiple poles at origin, means instead of k by s, now if you have a function k by s power n, that means k by j omega whole power n, then the slope of this particular factor, there are multiple poles, then the slope is not just minus 20 dB per decade, but it is minus 20 n dB per decade, where n is number of poles at origin. So, if it is 2, then slope will be minus 40. If n is 3, slope is minus 60 dB per decade. Similarly, the phase angle term for this phase angle term is, instead of minus 90, simply there is an n in the function. So, minus 90 n means if there are 2 poles at origin, the phase angle will be minus 180 degree straight line. Still it is independent of frequency. Now, let us see the Bode plot for derivative factor. The meaning of derivative factor, if you consider the function as k and 0 at origin, k and 0 at origin. So, g of j omega is k times j omega, and this can be written as 20 log k omega is the magnitude term, it is represented by a, and the phase angle of g of j omega is plus 90 degrees. Magnitude is expressed in decibels. Now, if you take that magnitude a is equal to 20 log k omega, I want to see for different values of omega how it changes. So, say again omega equal to, let us have 0.1 by k now, and 1 by k and 10 by k and so on. You can even go for 100 by k. So, when you substitute here, a is equal to, for this value of omega, 20 log k into 0.1 by k. So, it is 20 log 0.1. So, this will be minus 20 dB, minus 20 dB. Similarly, when you substitute 1 by k in the function, you will have 0 dB, and when you substitute 10 by k in the function, you have plus 20 dB, and if you substitute 100 by k, you will have plus 40 dB. So, what do you understand from this variation is, consider the magnitude in decibels on y axis and frequency again on log scale on x axis. So, the value, if you start from 0.1 by k, 0.1 by k say somewhere here, for omega. This is omega on log scale. So, for 0.1 by k, the value of the magnitude is minus 20 dB, minus 20 dB here. Next, when you change omega equal to 1 by k, the slope becomes 0 dB. This is 0. Now, when omega equal to 10 by k, the slope will be plus 20 dB, plus 20 dB, and further if it goes 100 by k, you have plus 40 dB. That means derivative factor magnitude also a straight line, but it has a slope of increasing with a slope plus 20 dB per decade. So, we say that the slope of this straight line, I mean derivative factor magnitude having plus 20 dB per decade. As I indicated, per decade means frequency increasing 10 times, the magnitude is changing plus 20. So, plus 20 dB per decade is the slope, and that derivative factor magnitude is 0 when omega equal to 1 by k. When omega equal to 1 by k, the magnitude is 0. Once again, if you see that phase angle versus the frequency, same scale is being considered for phase angle, and the phase angle is plus 90 degrees, straight line once again for this derivative factor. If there are more zeros at origin, so instead of k into j omega, but you have multiple zeros at origin. So, n indicates multiple zeros at origin, then the slope of the magnitude term is plus 20 only, but n is added to that, n dB per decade, and the phase angle phi is plus 90 n. It is again straight line, but it depends on the value of n. So, let us see how the magnitude and phase plot can be drawn for first order denominator term. First order denominator term, that means the g of s is given by 1 by 1 plus s tau. So, the sinusoidal function is given by 1 by 1 plus j omega tau. So, as this is a sinusoidal function, it consists of magnitude as well as phase angle, and this is given by 1 by under root of 1 plus omega square tau square, and the phase angle minus tan inverse omega t. So, the magnitude A is nothing but magnitude of the function in decibels. So, I need to apply 20 log to this function under root of 1 by 1 plus omega square tau square. So, this can be written as minus 20 log under root of 1 plus omega square tau square. I have taken the denominator term to the numerator, so minus sign will appear in the magnitude. Now, you can see that this magnitude term depends on omega. So, let us consider a case 1 at very low frequencies, the value of omega tau is very much less than 1 in the square root. Then the value of A is minus 20 log 1 I can approximate, and this value is 0. So, at very low frequencies, the contribution of the denominator term is 0 dB. Second case, we consider very high frequencies, because the magnitude plot is being drawn for wide range of frequencies. So, at very high frequencies means the omega tau is very much greater than 1. At very high frequencies, I would like to see how this denominator term magnitude varies as a function of omega. So, I will consider that omega tau is very much greater than 1 because high frequencies. So, the magnitude term A can be approximated to minus 20 log omega tau. So, how this term varies for different values of omega. So, at omega equal to 1 by tau and omega equal to 10 by tau, omega equal to 100 by tau, and so on. So, at omega equal to 1 by tau, the magnitude minus 20 log omega equal to 1 by tau into tau. So, it becomes log 1. So, the magnitude is still 0 dB even at this value. Now, at 10 by tau, if you calculate minus 20 log 10 by tau into tau. So, this is minus 20 log 10. So, the value is minus 20 dB, minus 20 dB. So, and 100 by tau, if you calculate, this will be minus 40 dB. So, at very high frequencies, the denominator term has a slope of minus 20 dB per decade. So, if you try to draw the plot, for this term A in decibels and frequency on log scale. So, initially it is 0 dB line, initially it is a 0 dB line. You can see that it is 0 dB, but at omega equal to 1 by tau also it is 0 dB. Say this is omega equal to 1 by tau, still it is 0 dB. Now, as omega further increases from 10 to 100, when omega is 10 by tau, it has a slope of minus 20 dB, and when it is 100 by tau omega value, then the slope is increased to minus 40. So, that means at high frequencies there is a line having some slope for this term, and at low frequencies it is having 0 dB line. So, when I have considered two cases, at very low frequencies a 0 dB line, that means between 0 omega up to 1 by tau it is a 0 dB line, 0 dB line, and between 1 by tau omega up to infinity for high frequencies it has a slope of minus 20 dB per decade. So, I can assume that the Bode plot for this denominator first order term has two asymptotes. These two lines, this is a 0 dB line for low frequencies and this is a minus 20 dB per decade line at high frequencies. Both the lines will meet at one point, that is at omega equal to 1 by tau, is known as corner frequency. Corner frequency. Corner frequency definition is the point where the two asymptotes will meet. Which two asymptotes? A low frequency line and high frequency line. So, the Bode plot, actual plot is something different, but we can assume that these low frequency and high frequency lines are asymptotes to the actual Bode plot, and I want to know that these two lines, where will they meet? They meet at some point omega equal to 1 by tau, that is given from the function itself. So that point is known as corner frequency. So if I want to know the magnitude at corner frequency omega equal to 1 by tau, so substitute this value in magnitude a minus 20 log under root 1 plus 1. You are substituting omega equal to 1 by tau. So this value is, you have minus 3 dB. The meaning of this is the magnitude is at omega equal to 1 by tau is not 0. It has some value that is minus 3 dB. Means you can see here minus 3 dB is somewhere here, minus 3 dB, and at omega equal to 1 by tau the magnitude is not 0, but it has minus 3 dB. So the actual Bode plot is drawn this way, start from origin, join minus 3 dB point, and then go like this up to high frequencies. So you can consider that this low frequency dB line and high frequency dB line are the asymptotes to the actual Bode plot, where actual Bode plot will go via minus 3 dB, because the value of magnitude at corner frequency is minus 3 dB. Let us see for the first order numerator term now, how the magnitude and phase angle plot varies with omega for first order numerator term. G of s is equal to 1 plus s tau, and whose sinusoidal function is 1 plus j omega tau. Now the magnitude A is 20 log under root of 1 plus omega square t square. Compared to the previous one, the only change is there is no minus that appear in the magnitude term. So you can see that A is equal to plus 20 log and same term that appears in the denominator term. So here also you can have two cases to be considered, that omega between 0 and 1 by tau, where tau is the time constant of this numerator term, and second case is between 1 by tau and infinity, low frequency range and high frequency range. So during this range, if you see the magnitude, it will be 0 dB. It will be a 0 dB line. And for high frequency range, if you see the magnitude, it goes with plus 20 dB, plus 40 dB, plus 60 dB, and so on, as the frequency is increasing 10 times. So the plot is again having a slope of plus 20 dB. It starts from 0 dB. So at low frequency range, it is 0 dB line up to omega equal to again 1 by tau, and at this point it starts increasing, having a slope of plus 20, that is 10 by tau, 100 by tau, and so on. So I say that this line is having plus 20 dB per decade. So numerator term or the 0 at non-origin will have plus 20 dB per decade at high frequency range, and if you want to see that exact value of the magnitude at omega equal to 1 by tau, so 20 log under root of 1 plus 1, once again this will be 3 dB. So the magnitude at omega equal to 1 by tau is not 0 dB, but exact value is 3 dB. So, the actual Bode plot starts from origin, it goes through plus 3 dB and goes this way. That is why this 0 dB line is called low frequency line or asymptote, and this plus 20 dB per decade line is a high frequency line asymptote, and these two asymptotes will meet at omega equal to 1 by tau once again. This is known as corner frequency. So, the significance of corner frequency is that the two asymptotes are meeting at 0 dB point, but the actual value of the magnitude at corner frequency is plus 3 dB in the case of numerator term. So, the last term that appear in Bode plot is a quadratic term. Quadratic term means it is a second order function. Second order function, if it is a term denominator, quadratic denominator term, then this will have a slope of minus 40 dB per decade for high frequency range, and here also you will find 0 dB line and high frequency dB line, but the corner frequency for this second order term, corner frequency for the second order term is omega n, that is undamped natural frequency that appear in the quadratic term should be taken as a corner frequency, but slope is minus 40 dB per decade. If it is a numerator term, the slope will be magnitude line will be plus 40 dB per decade, numerator term, and the corner frequency is again same as undamped natural frequency of this numerator term. So, no much change in the magnitude plot even if it is a second order term, because slope only is changing. If it is a denominator term, minus 40 dB per decade, if it is a numerator term, plus 40 dB per decade. This way drawing the magnitude plot is little complex because you need to convert the magnitude in decibels. So, you are applying 20 log and then taking the frequency on log scale, and the magnitude plot is to be constructed in this fashion.